way to like keep track of full static sections to see if anything is getting overwritten?
Okay, so the question is, I think, can you tell when variables are incorrectly written? Right? Not with GDB. With Valgrind, you can sometimes detect it. Valgrind will run this program very differently, so there's a good chance that you won't observe it. But if there's a sort of a static error in here, like that just manifests seldom, but say you're always going over bounds. Maybe the number of free list entries we're allocating is smaller than whatever we're initializing, so it's always just blowing over. Then Valgrind would find that. If you have a specific memory location in mind, then there's something called Watchpoint. It's not a breakpoint, it's a watchpoint. It's hardware supported, where you tell the CPU that, oh, anytime you access this address, just have an interrupt. That can be really useful, but in this case, there's lots and lots of these allocations. They're all over the place. We don't know which one's gonna fail. So it would be hard to use a watchpoint, I think. It also would tend to slow things down a little bit. And there's a limited number of watchpoints the CPU can support, like a handful. I haven't used them much. That's a good question. Okay, so next up, today will be kind of a mixed bag of topics. Next up, we should talk a little bit about the next homework, which is this vector thing. So I posted it. Let's just find it. It's quite similar to what we did in class last time. And chances are you will go through similar struggles as well. But then there's a little addition toward the end to make it, not just copy it from the lecture. Right. So the general idea here is we're writing some vectorized code. We're going to use AVX2, which is only available on one of our machines. That's the biggest one that we have. That's 128 thread Broadwell. So you can't use, well, you're still welcome to sort of log into the Kent fields and words and lines, but you can't actually run this code. You'll get a illegal instruction or something like that if you try to run code compiled with -m AVX2. So this should work the same. I don't think access has been enabled, but that'll be done shortly. What's that? Yeah, okay, yeah. We're gonna have to keep that access relatively brief, because that's the main machine we use for research purposes too, but there's no good way around it. If you have a CPU that runs AVX2, that has AVX2, you may as well use your local one. This is a single-threaded program. There's no need to use this fancy server as long as you have AVX2. The sort of format of the homework is the same as always. We're writing some programs, we're measuring their performance, we're making some plots, drawing conclusions. So in this case, there's a couple of performance baselines. There's this array minimum that we did in class. So, but the baseline is just a C program. So for loop, run through, find the smallest value. And then you want to, there's actually a makefile that let's find that. Yeah, so this makefile has a couple of tricks in it. This one here says for the no-vec, it just disables vectorization. So we run the same C program compiled with and without vectorization to see how that how it differs. So there's the one. Find the minimum with a normal little C loop. and then find the index of the smallest value in a little C loop. And that's quite different. You'll probably find that the vectorization doesn't help much for that one, because the compiler can't figure it out. And that, of course, leads us to the next step. We start by doing this iterative vector min. This is the same thing that we did in class. You may find the lecture helpful. Basically, we use this existing instruction called VP min SD that gets the minimum out of 8 integers. Right? So you have an array of 8 small values, and then we, out of those 8, one of those is the absolute minimum, and we do some sort of shuffling to kind of figure out which one is the actual smallest out of those. That one should be easy. That's just kind of fighting the compiler a little bit to make, like getting your syntax right and so on. And because I know the instruction set is huge and difficult to navigate, I have added, provided sort of the instructions that you probably want to work with. You're more than welcome to try other ones. There's lots of options, but you could look into those. And then if you use this Felix Cloutier, this guy, has very good documentation. VP min, come on. Okay, so it's probably p min is where it's, yeah. So that's the one for the integers, and here is the VP min SD, so it says everything, and the full pseudocode for how it works. I find this pseudocode extremely helpful, because anytime you have a description in words or with pictures, I guess I get confused, but with this, there's no question of what's going on. Like, these bits are assigned these values, done. Right? So I strongly recommend that just to understand what the operations are doing. Okay, so that one's relatively easy, and we already did it in class, but the next one we didn't do in class. It'll be a bit of a puzzle. But there's no concurrency here. I mean, there's concurrency, but it's deterministic concurrency, which is nice. So basically, now we want to find the index of the smallest value. And there isn't an instruction that does this for you. In fact, there is an instruction, I think, that does it for some types within those 8. There's an instruction that can, for floats, I think, can find the index of the smallest value of those 8 floats. But that's not what we're looking for here. We're looking for the index over all these potentially millions of integers, find the smallest value. So how do we do that? We have to basically implement our own minimum, just like we did in C. How do you do a minimum? You say, oh, if it's smaller, then set the new minimum to the new value, right? But now we need to do it for 8 values at a time. Right? So that's slightly different. There's this greater than operation that'll set for all bits within one integer. Let's say, oh, if this integer was greater than the other integer, so we have these 2 8-wide arrays, right? So if that integer is greater than these integers, this integer, then they'll all be 1s, all the bits for that one. If that one is smaller than this one, they'll all be 0s. Right, so on. So you get a mask for free, sort of, out of this. That's really helpful. So now you have a mask that says these integers were the bigger, were smaller than the other ones in the other word, and these were smaller than the, yeah. So you have to kind of do this compare. You'll have to probably inverse the mask. You want to apply some AND and XOR, or AND and OR to kind of combine the two. It'll be a little logic, Boolean logic puzzle. But when you have it figured out, then you'll get a minimum. Well, actually, I didn't. Oh yeah, I suggested it here. If you start by just implementing the minimum, right, let's just say we don't have this min instruction, the VP min SD. Just implement it using the compare and such. Then you can see that you got it right. And once you have a minimum working, then you need to add this part that that also tracks what was the index. So every time around the loop, you kind of have to remember which time around the loop were we when we found this new lowest value. It'd be a fun puzzle. I think the assembly is not going to be too challenging because we have the assembly from the previous, from class. So the part that's challenging is just the logic puzzle here. You might want to watch out for the clobber list. That one's kind of important. If you're using any registers within the assembly code that aren't part of the input and output, like the %0, 1, 2, 3, you have to put them in the clobber list. Otherwise, the compiler doesn't know that you're using those and will put its own values in there and get all confused when you overwrite them. Okay, and we don't need to do that final, the suffix. We don't need to do that in assembly. Let's just do that one in C and not worry about it. Really, the performance is all, in this case, the performance is dominated by the loop and not the suffix. And then the final one is a bonus question. So say we have a fixed size array now. In this case, in fact, I forgot to put the wording here about the plots. I think I'll update it a little bit. There should be, of course, evaluation plot for each one to compare the performance of these solutions. But if you have a fixed size vector that you're wanting to find the min out of, then everything gets different. You don't need a loop anymore. We know how many elements there are. And if we know how many elements there are, then we can start worrying more about the timing. So to do this one you can spend a lot of time on. You can do something kind of simple, you can do something really clever, and the idea is, let's see, here. So once you have something that works, post the cycle timing on Piazza. Right? That way we can get a kind of keep track of what's possible here. All of the benchmark stuff, it outputs the number of cycles required per element in the list. And it should be considerably lower, I think, for this fixed size vector than for anything with a variable size vector. Right. So here we're back to sort of what we did in the midterm. Like, oh, the latency for a load is 3 cycles. So then maybe I can do the min of those two instead of the min of these, and fit things in. That sort of thing. If you like this sort of stuff, it could be a fun exercise. If you hate it, don't do it. Okay, that's it. Any questions on this thing? Yeah.
I was just thinking, like, could you get creative with using, like, maybe changing the integers that you're working with, so like they store the indices in there?
That's an interesting idea. So, in general, I think that's often worth exploring as a hack. In this case, you don't get to change the benchmark or test programs. So if you have time to get creative with the values within your function, then that's fine. If you were to store the index, let's see, I don't know if these test functions, I don't remember what the range of values were. I think it's up to 1024 only. So yeah, in principle, maybe you can stick an index in there. Yeah, maybe I'll just leave it alone the way it is. And you can experiment with that. I think it'll be faster and easier to just have a kind of a running index and remember the index at which you find the new minimum. It's just some more bit masking, basically.
Do the Macs support AVX too? The new Mac?
Beats me. Yeah, mine does. I was running some things with AVX too. Yours looks like mine, but it's hard to tell.
Yeah.
AVX2 is from Broadwell and up. Yeah. And Broadwell is pretty old now. It's like a 2015 processor, I think. Okay, so I think the point of this homework is to get a little comfortable with this vector stuff, to kind of see what can the compiler do for us. Compiler can do a lot, but it's nowhere near what a person can do if we put our mind to it, right? So I think we should see substantial benefits from hand tuning this, hand writing this thing. Probably like a 5 times, 10 times speed up, something like that. 10 is probably optimistic, but probably 5. Okay, anything else on this one? If not, we'll use the rest of the time to start discussing GPU. GPU programming, I guess. Data parallel programming on GPUs. So, there's all sorts of parallelism in this class, right? I think the GPU parallelism is the most massive parallelism. There's the most things running at the same time, at least in the sense of what's described by the program. The program really has to be ridiculously parallel in order to fit on a GPU. So what we've done so far, we did threading. On one thread, we see, oh, there's some parallelism in order to speed up the one thread. And if we're clever, we can improve that. We can kind of take better advantage of that parallelism. That's good. And then we did some multi-threading, right? But we don't have that many threads. And each one of those threads can do a lot. Right? There's cache coherency in the memory subsystem. There's explicit synchronization operations. Each one of these threads has its own big piece of silicon, and it can run completely different code. And then we looked at this vector processing. Now we're back to single-threaded, really, but we're kind of widening the amount of data that one thread is operating on at the same time. It's a pretty awkward instruction set to work with, but I guess it's relatively doable for the compiler, so most of the time you don't have to worry about it. The compiler can kind of detect that this is vectorizable. That's good. But we don't get that much parallelism out of it. The most you can get is 32, I suppose. Like if you have 32 bytes in a 256-bit wide array, or with AVX512, maybe you can go to 64 bytes parallel. So if you have some absurd operation that needs to operate on individual bytes, but can do it in array form, you can get 64 times speed up. But in the GPU setting, you can do thousands. Right? So now you can have thousands of parallel threads. In fact, the way you describe the program is more than that. You probably describe it as millions of parallel threads. Everyone doing something really stupid simple with no interaction with the other threads, ideally. If you can describe your program that way, then the GPU can run it very fast. Let's take a look at the... Oh, I wonder if we can get a GPU silicon. I wonder what that looks like. Yeah, look at that. That doesn't look anything like our CPU, right? So each one of these is called let's see, is it a multiprocessor? Yeah. So in this is a Volta or a Tesla. I don't know the difference between them. So we have this is one chip, right? That goes on an extra board, usually that you plug into your computer. And that's a graphics processing card. Sometimes it comes in a laptop. It'll be in a separate chip, but still on the motherboard, or sometimes even you have an Intel GPU, it'll be integrated into the actual CPU enclosure, but probably on a separate chip, a separate piece of silicon inside of the same enclosure. Okay, so one of these has some links to the outside world, and then we have a relatively large shared piece of memory. It's called global memory or device memory. It says cache here. I don't know. I don't like that. Well, maybe this is the cache. I don't know why it's blue. This is not a complete silicon picture. It ought to be a real silicon picture. It's still sort of a graphic of it. I didn't spot that at first. Ah, no. Ah, is it? Okay. This is a mobile one. Okay, so anyway, the general idea is, let's just stick back to this one here. Oh, they're all the same. So we have some memory, device memory, which is it's called cache here, but this is not cache coherent with your CPU memory. The computer is separate from the GPU. So if you want your GPU to work on anything, you first have to copy the data over to the GPU into its own memory, which the CPU has no other control over. And then we have all these units. Each one of these is a multiprocessor. A multiprocessor is sort of like a processor, sort of like a vector processor, you could say. It runs one instruction at a time, but interestingly, inside of the multiprocessors, lots of little ones, they all run the same instruction. So sort of how we do in vector instructions, where we apply the add to all these 8, right, at the same time. In a multiprocessor, you run the same instruction for different data. So you might, if you have an array, these instructions might add, like the first processor adds for the first element in the array, the second processor adds for the second element in the array, and so on, right? So we do all the array elements at the same time. Okay, so there's a number of these multiprocessors that will vary depending on your GPU. This is one of the complicating parts of GPU programming. The architectures vary quite a bit. There's different manufacturers, there's different instruction sets, and from each manufacturer, there's different numbers of multiprocessors and the processors within them, and so on. You want to be able to write a program that works on pretty much everything. I guess it's a little related to when we start doing this architecture-specific programming on the Intel CPU with multi-cores. We don't know how many threads and so on. There's some relationship, but it works. Okay, so each one of these then, together, in lockstep, execute the same instruction. And then you have another multiprocessor. That one is not dependent. That can execute a different instruction, potentially, than these. But generally, how we express the program is, all you guys run the same program, very small, simple program, all for different data. So there's your shared memory, device memory that each multiprocessor can access directly, sort of like normal global variables. And then there's inside of here, there's maybe it's this. There's this is called shared. This is device. This is shared or local. And then for each processor inside of here, we also have private. There's stuff that no one else can see. The host, the CPU, can access only this by sort of memcopy type operations. So you say, you can tell the GPU allocate this much memory, and then you can say, okay, we'll ship this gigabyte array over there, and then you do your work, and then the memory, maybe you'd allocated a results array somewhere else, you can memcopy the results array back. But the GPU really doesn't have much other control over what all these other, what all these little processors do. Okay, so how do we program this thing? Well, let's see. I think I had a nice picture. Yeah. Oh, sorry about the resolution. So basically, GPUs will only work on programs that take this form, on problems that can take this form. So we describe our problem as an array of some number of dimensions. Could be just a line of a bunch of, like a single dimension vector. Could be 2 dimensions, as in a picture. Sometimes it can be 3 dimensions. There's a limit. Different GPUs support different numbers of dimensions. I think 3 is pretty popular for sort of physics simulations and such, so probably it supports 3. But 4 or 5, I would imagine is less common. Okay, so we have this, let's think of it in 2 dimensions. It's a picture. So what do we want to do with this picture? Maybe we want to apply a mask, a threshold. So it's a grayscale picture. If the value is 128 or more, it should go to 255. It's lower than 128, it should go to 0. So what we do is we give the GPU the whole picture, and it has to be a square. At least this one suggests that it doesn't, because they have different variables here. But from what, at least in the API that I looked at, it seemed more like it has to be a square. Anyway, so we give it the whole picture, and then there's some advantage to dividing this up into chunks. So we had these multiprocessors, right, that all execute the same instruction together. The multiprocessor has some shared memory. There's a barrier operation where we can run all the processors and then wait until all the processors are done with their work before continuing. So you can do some minimal coordination between processors in a multiprocessor. And there's also some memory locality benefits to working on data that's nearby within one multiprocessor. So the work item, is the pixel in this case, right? We have one pixel that we want to see what was its value, and then set in the resulting array, set it to 0 or 1. Maybe just override it to 0 or 255. Work item is a single pixel, and the word group is a chunk of the picture. If you think about cache lines, right, it would make sense that the pixels that are next to each other are worked on by the same multiprocessor. So now this picture moves into the GPU, and then one multiprocessor starts working on a piece of the picture, and if it's a grayscale image, you can fit 8 pixels next to each other, right, to make one cache line. If they have 64-byte cache lines, I don't know. But this memory locality is something we want to take advantage of. So we group up this thing into a bunch of groups. So maybe we make it here 4x4 pixels, 8x8 pixels. And this says all of these items, all of the work items within one of these chunks should be operated on by a single multiprocessor. So with a larger work group, you get better memory locality, but there's a trade-off. Right. Say our picture, we divide our picture up into 4 work groups. You only get to run that on 4 multiprocessors. If you have an expensive, fancy GPU, you might have hundreds of multiprocessors, depending on the architecture. So you want to divide it up somehow to match what your architecture is, probably, but at least have many. If you make them too small, if the work group is 1, then there's no memory locality benefit and things run slower. That's the sort of trade-off. Okay, so the programming model is basically we write a function that knows which work item it is. It has its index. So it knows which pixel, in this case, that it needs to work on. And then it just refers in, it gets a pointer. Your function gets a pointer to the picture, figures out, oh, I'm pixel 522, so I'll go and load the value from 522, see if it's big enough, maybe set it to 255, maybe set it to 0, and then return. That's the whole program for the processor. But this is a little weird, right? Because I said that all of the processors within one multiprocessor execute the same instruction in lockstep. So how are we going to do that? Right? We have a branch. So for some of the pixels, they go left and they set it to 0. For some other pixels, they go right and they set it to 255. What's going on? How can we implement that? This is actually allowed, right? The GPU language, and we'll get to some of the details, but it supports branches. It'd be kind of lame if it didn't. So it is still true. It executes only one instruction at a time, but it can put some of the processors to sleep, basically. So say in this work group here, we're running maybe 64 pixels at a time, 64 processors within one multiprocessor, and then 100 of those multiprocessors. Now we can run 6,400 pixels at the same time, right? That seems like reasonable parallelism. But within this thing, half of the pixels need to go black. The other half needs to go white. So the scheduler, well, the processors, they all run a compare. And they see, oh, I need to go left, right? And the other half of them see, I need to go right. So now the multiprocessor will schedule one of those two. So all of the ones that need to go right, where the branch was true, they now execute. And they probably finish the job. Right? And then we run the other ones. The remaining processors that needed to go left in the branch, and they will run. So it takes twice as long, right? Because we have to run twice as many instructions. First we run these, and then we run these. They'll take twice as long. So ideally, you would have your work group sort of put together so that they all go the same way. If you already know they're all going to go the same way, that'll run really fast. And then your multiprocessor can move on to the next work item. So if there's, like, we have a picture that's all white over here and all black over here already, it'll run really fast. You run, just blow through one work group at a time, and then the larger chip scheduler will say, okay, this multiprocessor is done, take that work group, finish that one. So. Okay, so overall then, we have, at the top level, we have a bunch of these work groups that get scheduled sort of asynchronously onto the multiprocessors. Whenever a multiprocessor finishes with a work group, it gets another work group to work on. And inside of the multiprocessor, there's all these work items. Same thing there. A bunch of the work items get scheduled, depending on how many processors are available. And as they finish up, we schedule the remaining work items onto the processors. It's all sort of abstract, and it kind of needs to be abstract because there's so many different technologies that are supported by this overall scheme. So you can run this on a CPU. Right? Any program like this you can run on a CPU just fine. It's just a ton of threads. And you don't have to spin up P threads for all of them. Just run one piece at a time and you're done. It won't be nearly as fast as the GPU version. Okay, so how do we program this thing? Let's see. So we have work group that maps to a multiprocessor. Contains work items to individual processors. And problems always specified as an n-dimensional array. Okay, I think I'll take a quick look at an example. I think this will be easier than just talking about the concepts. So, all right, maybe there's one more piece we need to know. The GPU doesn't know x86. And it doesn't do a lot of things. For example, it would be very awkward to use a function pointer, right, in a GPU context. Because now suddenly, you don't know anything about which instructions each of these processors should run. It used to be, oh, they have this set program, we go down like this. Sometimes one has to wait, the other one goes on. But now suddenly, with a function pointer, you go all over the place. And yeah. So that's not supported. There's a lot that's not supported, actually. Of course, you can't access main memory. You can't access the local memory of another thread. It's just no way to describe it. There's no recursion. There isn't really a stack in the same. Well, maybe there's a little stack, but it's not like a general purpose stack like in a CPU where you can go as deep as you want, really. So you can't have recursive programs. You can call another function, I would think. Pretty sure. But stack depth is strictly limited. Okay, so now how do we write this program? It doesn't even run x86 code, so we need to compile it somehow. There's actually two different ways we can write programs for GPUs. There's two different sort of tool chains. You may have heard of them. One is called CUDA. That's proprietary for NVIDIA. And then there's OpenCL, which is kind of general purpose open source thing. We're going to be working with OpenCL. CUDA is probably a better choice if you are trying to tune specifically for a given GPU. Because it kind of maps more closely to the actual architecture, so you might have a little better control over what it actually does. There's no sort of cycle tweaking equivalent for GPU programming. It's not. We don't even know which instructions it executes. That part isn't exposed. Okay. So anyway, we're working with OpenCL. And the general idea is you write a host program, normal C program, and then we have a device program, which is written in OpenCL. OpenCL is a restricted version of C with some extra bells and whistles. So you can do things like that, and that means I should make sure I have the right terminology here. So this means, allocate this array, or let's have this whatever variable it is, should be local to the multiprocessor. Or if you say global, it's actually addressable by all of the multiprocessors because it's in that big device memory. Or if you make it a private, which is by default, that's more like a register or a local variable. It's only available to the individual processor. Other processors can't see these variables. There's no way to sort of pass an address to this to another processor. Okay, so we write a device program in OpenCL, and then we, at runtime or at compile time, we tell this OpenCL runtime to compile the OpenCL program and then ship it over to the GPU. So you can actually give it source code, and there's a function that takes the source code even just as a string, and it'll compile it on the fly and ship it to the GPU, and now you can call it. Okay, let's see what a very simple program looks like. This is a program, it's called a kernel. Kernels is what we always work with GPUs. The kernel is the little program that runs on a work item. This kernel takes four parameters, 3 global arrays, and we just want to add. Like, there's 2 input arrays and an output array. C is the output array, and we want to add A to B and put it in C. So normally, we would write it with a for loop, go through all of them. That's not the idea here. Now we say apply this kernel to the problem set, which is these 3 in parallel. And the kernel is basically, here it was hard to, we don't know that the arrays are the right size. Like maybe they're not square, and they're not exactly like some multiple of whatever the device size is, workgroup size. So as long as it's our ID falls within the size of these arrays, just compute the sum. Some things are special about this, right? It looks pretty much like C. It's very similar to C. But here we say this is a kernel. So this is OpenCL specific. And then we say those are global variables, and this will arrive as a private integer. So you can't take the address of this n. It doesn't have an address. Or at least it doesn't have an address that you can pass to somewhere else. Okay, so that's the kernel. Super simple. Writing kernels, not a big deal. They tend to be really dumb. Getting it to actually run this thing, less simple. Quite a bit of overhead, and if we do get around to doing a homework on this thing, we'll evaluate this against other types of parallelism to see when it makes sense. So if we want to compute a min, probably makes sense if we have 1 billion integers, right? We can probably do a pretty quick min using this kind of parallelism. But if we have 10, maybe not. Right? And then where does the line go? That's a little unclear. When you see the code for vec add here, you see what I mean. Okay, so this is just some setup to kind of set up the problem, right? We have those arrays. These are allocated on the host. So there's just some numbers to add. Nothing special. So then it gets a little more interesting. So in order to actually do any of this, first we have to figure out, is there a GPU in this machine? Right? So that's here. Or we get, I don't know what platform. Little iffy on that. Okay. Then we get a list of these GPUs. So in this case, we're only interested in one device. But this lists out all of the GPUs available on the machine. And in fact, it's not just GPUs. It also lists the CPU, because that one can also execute this kind of program just fine. All right, and then we say, OK, I'm interested in the GPU. So we picked one that's just a GPU. So now I have a context that I can work with to do things with the GPU. The main thing you want to do is create a command queue. This is how you talk to the GPU. There's basically 3 things you can do, maybe 4. You can do a memcopy to the GPU into the device memory. You can execute a kernel. You can do a memcopy from the device memory into host memory. And you can wait for something to be finished. Basically, think of it as an M fence, I guess, or a barrier. So the command queues can be either in order or out of order. If they're out of order, they'll be faster, but then it'll be asynchronous, so you have to have explicit synchronization that you add, like you say, oh, wait for this to finish, like CL wait. Say. Okay, so we have a command queue. And then there's this. Create program with source. So we got somewhere earlier, we just loaded the contents of that file into memory, the add.cl. So now it's compiling the program, and here we're pulling out oh, there's compiling the program. Then we're pulling out one kernel. So now we have a pointer to a function that we can run, basically, on the GPU. Allocate some memory on the GPU, some buffers, and here we tell the command queue to copy the contents of A and B to the device equivalents of A and B. So there's no writing directly, like you don't have a for loop that accesses directly this device memory. You say, like, mem copy this thing, that's all. The driver supports this big mem copy. Okay, so we allocate memory on the device, we copy over those two argument arrays, and then we say the parameters that are passed into the kernel, like the A, B, C, right, and the size of the array. Finally, run the kernel, right? Say the kernel, and then we're passing in, like, what should be the size of the work group within this, and how many items do we have total. Wait for it to finish, and then read out the results. And then I think we're done. Right, and clean up some. So you see there's quite a bit of sort of setup here. So if you want to do a small amount of work, probably not worth it. If you're really memory bound, not sure, depends a little bit. The CPU has really good memory bandwidth, so we'll experiment with this in the coming lectures, I think. All right.
What
Yeah.
sort of clock cycle does the GPU have compared to?
They will be in the gigahertz range, but I don't know exactly.
Sounds like a neural net. I left my